So, here's a wild thought for you. Could a hacker literally stop your car in its tracks just by messing with your tires? It sounds like something straight out of a spy movie, but it is a very real threat. Today, we're going to dive into a brilliant piece of engineering that keeps you safe on the road, and it all comes down to a tiny 8-bit chip and some seriously clever math. I mean, it sounds pretty far-fetched, doesn't it? But it's a totally legitimate question. See, every new car has what's called a tire pressure monitoring system, or TPMS for short. It's actually a mandatory safety feature. It uses these little wireless sensors inside each wheel to let you know if a tire is running low. But that very same wireless signal that's designed to protect you, well, it also opens up a sneaky little backdoor. And this backdoor has a name. It's called packet spoofing. Basically, an attacker could just be sitting by the side of the road and blast out fake radio signals that look exactly like the ones from your car's tire sensors. If they send a fake low-pressure warning, they could trick your car's computer, light up your whole dashboard, and basically force you to pull over. It's a denial-of-service attack, but it's not targeting the car's electronics. It's targeting you, the driver. So, how in the world do you defend against something like that? That's the real engineering puzzle we're going to get into. The issue wasn't just spotting the threat, but figuring out how to shut it down inside the incredibly tight constraints of a tiny little tire sensor. Now, if you know anything about cybersecurity, your first thought is probably what everyone thinks. Just encrypt the signal, right? Slap a standard, powerful cryptographic algorithm on there to lock down the communication. Problem solved. Easy peasy. Well, not so fast. So here's the first massive roadblock. The software on the tire sensors that were already out there, it was already using more than 98% of its available code space. There was literally no room left to just cram in a big, heavy encryption library. The digital real estate was pretty much maxed out. And remember, all this code is running on a tiny, battery-powered 8-bit microcontroller. These little guys are built for one thing, extreme efficiency, not for heavy-duty number crunching. Trying to force a standard encryption solution onto this chip would be like trying to perform surgery with a sledgehammer. It's just way too big, too clumsy. It would completely crush the system. A different tool was needed, a much, much sharper one. And this is where the genius comes in. When you can't use a hammer, well, you invent a scalpel. Instead of some brute force solution, the engineers designed a super lightweight, really elegant protocol that gives you all the security without any of the heavy overhead. The heart of this invention is something they called an authentication marker, or AUM. The best way to think of it is like a secret handshake for every single little chunk of data that gets sent. It's this dynamic digital signature that changes with every single transmission, and it proves the message is from the real sensor. And the best part? It does it all with simple, efficient math that the tiny 8-bit chip can handle, no problem. Okay, let's walk through just how clean and simple this logic is. First up, step 1. The sensor in your wheel and the computer in your car are generating the exact same sequence of pseudo-random numbers. They are perfectly in sync. Then, step 2, the sensor calculates a standard data check value called a CRC. That's just a fancy way of saying it creates a digital fingerprint to make sure the data hasn't been corrupted. Now, step 3 is where the magic really happens. It takes that random number and that CRC and combines them with a super simple operation called an XOR to create the authentication marker. And finally, step 4, the car gets the message, does the exact same XOR math with its own synchronized random number, and if the result spits out the original CRC, bam, it knows the packet is legit. The XOR operation is both the lock and the key all in one. Okay, so the logic is really solid. But, the real world is messy. What happens if you drive through a tunnel and the car misses a few signals from the tire? The sensor's random number generator would keep ticking along, but the cars wouldn't. They'd fall out of sync, and then the car would start rejecting perfectly good signals. The security feature would actually end up killing the whole system. Not good. And this is absolutely crucial. A clever idea is one thing, but making it strong enough to work reliably out there in the chaos of everyday driving, that's what turns it into a real-world solution. So how did they solve this desynchronization problem? The answer is another piece of beautiful logic, something called a sliding window. So when the car gets a packet that doesn't match the random number it's expecting, it doesn't just throw it away. Instead, it intelligently searches a small window of possibilities, a few numbers forward and a few back in the sequence. If it finds a match inside that window, it instantly resyncs its own generator and accepts the packet. It's a brilliant way to keep things secure without sacrificing reliability. And it's that robustness, that ability to self-correct and handle all the little imperfections of wireless communication that elevates this whole thing from just a cool idea in a lab into a practical, commercially viable, and patented invention. It actually accounts for the physics of the real world, not just the perfect world of math. So, what's the big takeaway from this whole story of the 8-bit scalpel? Well, it's a really powerful lesson about engineering and innovation. Often, the most elegant and creative solutions don't come when you have unlimited resources. They happen when you're forced to solve a really hard problem with really tight constraints. That total lack of memory and processing power, it forced a much more creative path. And that really just leaves us with this final thought. In a world where we have massive cloud computing and what feels like infinite resources, the story of this 8-bit scalpel is just this powerful reminder that there's a unique kind of satisfaction, a real elegance that comes from working with constraints. Being forced to invent a scalpel instead of just swinging a hammer didn't just solve the problem, it did it in a way that was smarter, more efficient, and, let's be honest, way more impressive. It's a great reminder that sometimes having the biggest box of tools isn't nearly as useful as having a sharp, focused mind.